Our exploration of rotation has closely followed how we've learned physics during this year. We started off with how objects move and looking into rotational kinematics. And then we went into why objects move and specifically why they rotate. And instead of looking at the concept of force, we found the rotational analog in torque. And the thing is that beyond this point earlier in the year, we discovered there were other ways we could analyze the same sorts of problems. And some of these ways would be simpler in some situations and harder in others. And we're going to do that for rotation too. And we're going to first do that by moving beyond what we did earlier, which was momentum, to the rotational analog of momentum, otherwise known as angular momentum. Now, the first part of this video is going to be a lot of review because we're going to find out that angular momentum in a lot of waves behaves much like linear momentum, but there are some very key differences that we have to note as well. Well, let's start with what was momentum. Well, momentum is a measurement of inertia and motion. In other words, how much mass an object has and how much motion it has. And we calculate it with P equals mv, where P is the momentum in kilograms meters per second, simply equal to the mass times the velocity. Not to mention it is also a vector, meaning it has both magnitude and direction. And while we went into quite a bit of detail of momentum, we didn't regularly note that really we should have been adding this word linear to everything. That equation, P equals mv, is really the linear momentum of an object. But there is a rotational analog to linear momentum, which we abbreviate with a capital L. And angular momentum is just a measurement of rotational motion, specifically telling us how much rotational inertia an object has. So that includes its mass and the distribution of that mass, and how much spinning motion or rotational motion the object is currently exemplifying. Alright, well if that's the case, we should be able to figure out what the equation is for angular momentum, and much like we had momentum, linear momentum was mass times velocity, we have angular momentum is the rotational equivalent of mass times the rotational equivalent of velocity. So L is equal to I omega, where the angular momentum is in units of kilograms meters squared per second. And that is a bit of a mouthful of a unit, but it's just really the units of the other two combined because it's equal to I times omega, where I is the rotational inertia in kilograms meters squared, and omega is the angular velocity or the rotation rate in radians per second. And additionally, angular momentum is also a vector, and typically we say if it's in the counterclockwise direction, it's positive. If it's in the clockwise direction, it's negative. So let's say we had a disk with a mass of 2 kilograms and radius 0.25 meters, just like we see here. And we can rotate in 3 different ways. In scenario A, it rotates counterclockwise about its center at a rate of 5 radians per second. In scenario B, it rotates clockwise about its center at a rate of 8 radians per second. And in scenario C, it just sits at rest. So let's go ahead and calculate the angular momentum here. But to do that, we need to know what is the rotational inertia of this disk. So I'm going to go look at my table, and for a disk, it's I equals 1/2 mr squared. So we're going to replace the mass in the r, and we end up getting a rotational inertia of 0.0625 kilograms meters squared. And from this point, it's pretty straightforward. For scenario A, I'm just going to multiply that I by the angular velocity, which is positive 5 radians per second because it's in the counterclockwise direction, and we get a angular momentum of 0.31 kilograms meters squared per second. Positive meaning it's moving counterclockwise. For scenario B, we're going to multiply that I by negative 8 radians per second, negative because it's clockwise, and we get negative 0.5 kilograms meters squared per second. But what about scenario C? Well, if it's sitting at rest, that means it is not rotating. If it's not rotating, the measurement of its rotational motion will just be 0, and therefore the angular momentum will be 0. An object must be rotating or revolving to have angular momentum, just like an object must be moving through space to have linear momentum. Now, we re-express Newton's laws of motion in terms of linear momentum, and we're going to see that there are some rotational analogs which will help us conceptually think about angular momentum in a bit more detail. So Newton's first law of motion basically just tells us that if the forces on an object are balanced, the momentum of the object remains constant because we have no net force, which means we have no acceleration, and if you have no acceleration, there's no change in velocity, so the momentum will be constant since the velocity is constant, and the change in momentum will be 0. The angular version of this looks very similar, but instead of having the forces on an object balanced, we're going to have the torques on an object balanced. If those torques are balanced, we're going to have no angular acceleration. If we have no angular acceleration, there's no change in angular velocity, so the angular momentum will be constant. The change in angular momentum will in fact be zero. So let's take a little bit of a tangent to actually see what this can tell us about a particular situation. Let's say we had some ball that was just moving through empty space. Say this is far, far away from Earth, and it's moving at some velocity v. And that since it's far away from Earth, there's no gravity or anything like that, the net force on this ball will be constant, meaning that the momentum of this ball will be constant. And we learned back in the linear momentum unit that basically, if we have this scenario, well, then the center of mass will be at the center of the ball, and if the forces are balanced, well, therefore, this center of mass is going to continue moving at this velocity v, because that center of mass will move at a constant velocity as long as there's no net force. Okay, that's all making sense so far. But let's say this ball wasn't just moving through space. Let's also say it was spinning with some angular velocity omega as it moves through space. Well, if it's spinning and it's far, far away in space, well, there's really no net torque on the object. And if there's no net torque on the object, well, then that angular momentum will need to stay constant. And the object is going to be continually spinning as it moves through space. And in fact, we would see that's the case, that the ball would be spinning as it continues to move forward. All right, this seems pretty straightforward. But what happens if we have a scenario with an object that's a little more irregularly shaped? Like imagine, I guess an astronaut lost this hammer way out in the far out reaches of space. Well, let's go ahead and mark where the center of mass of this hammer is. It would be really close to the head of the hammer because that end of the hammer is heavier than the rest of it. And if we say it's moving through space at some velocity v, well, the net forces on this hammer are zero because it's way out in space. So the momentum of this hammer will be constant, and if it's constant, well, then the center of mass of the hammer will continue to move forward at this constant rate. What if this object was spinning once again? Well, if it's spinning, once again, there's no net torque because there's no forces at all on the object, and so the angular momentum will be constant and it will be spinning through space. But what will it be spinning around? Well, obviously, to keep the center of mass going at a constant velocity, that must be moving in a straight line. So this object must be spinning around its center of mass. And so to kind of see what this looks like, if I take away these two diagrams here, if we saw it, we would see it doing this, and it may not be intuitively obvious at first, but if we were to track the center of mass, we would see it is in fact going in a straight line. Well, okay, let's say we change the situation up slightly. Let's say we took this hammer and we took it to Earth, and I basically took it and I chucked it across the room. Well, we know for a fact the net force on this hammer would no longer be zero, right? It would be taking a parabolic trajectory because the force due to gravity would pull it downward toward the ground. But that would be the only force on the hammer. And where is that force applied? Well, it's at the center of gravity of the object. Well, if that's the case, and that's the only force, well, then the net torque would continue to be zero, and it's going to continue spinning around its center of mass. And this is a trend we want to make sure we kind of have down. If we have any sort of rotating object and it has no fixed axis of rotation, in other words, there's no axle, there's no pivot, I'm not holding it at some point, well, then it's going to be rotating around its center of mass if it's moving through space and rotating. And this is something we do want to go ahead and get down because we're going to see more and more of these types of situations as this unit continues. Well, we said if the forces on an object were balanced, its linear momentum would remain constant. But if we take this and expand it to the second law of motion, in which these forces are unbalanced, well, then the momentum of the object will change. And in fact, we could define the net force as being the change in momentum, or linear momentum, with respect to time. And if we do use this equation and we multiply this delta t across, we end up getting the equation for something known as impulse. The impulse, which is that delta p, that change in linear momentum, is equal to m delta v equals to f delta t. Well, let's look at the angular version of this. If this is the case, if we have a net torque on an object, well, then the torques will be unbalanced and the angular momentum of the object will change. So the net torque is equal to delta L over delta t. That's in fact another definition for a torque is a change in angular momentum with respect to time. And we can also utilize something now known as the angular impulse equation. I'm once again going to multiply this delta t across and see delta L is equal to I delta omega, so the rotational inertia times the change in angular velocity, which will be equal to tau delta t, the torque times the change in time. But the key point I want to get across here, though, is that if we want to have a change in angular momentum, if this angular momentum, its rotational motion is going to change, there better be a torque applied. If this is changing at all, a torque must be present. So let's look at an example. Let's say that we have a propeller that's spinning clockwise at a rate of 8 radians per second. So this propeller, as we see right here, is like a rod with an axle through the center, so it's spinning around the center point. And we say that has a mass of 15 kilograms over here, and that 1/2 of the rod is 1 meter long. So initially it's spinning at this 8 radians per second in the clockwise direction, but then we apply a 120 Newton meter counterclockwise torque. We apply that to the propeller until it spins counterclockwise at 22 radians per second. How much time does it take for this to occur? Alright, so let's kind of start to look at this problem, start figuring out, okay, what do we know here? What are our givens? We already talked about the mass and the radius here. Now keep in mind, though, that we don't want, since this is a rod, we don't want the radius, we want the fact that the length is 2 meters. That's going to be crucial later. But if we look, we say that, okay, the initial angular velocity is 8 radians per second in the clockwise direction, so I'm going to say negative 8 radians per second. The final angular velocity is 22 radians per second in the counterclockwise direction, so positive 22 radians per second. And the torque on this object is a counterclockwise 120 Newton meters or positive 120 Newton meters. And I'm going to utilize this angular impulse equation. Delta L is equal to tau delta t equal to I delta omega. But we want to know how much time does this take. So we want to isolate delta t. So I'm going to go ahead and divide tau across. So I have I delta omega over tau. So how can I figure out this delta t? Well, delta omega, I've got enough information there. I have enough information for the tau. But we need to know how to find the rotational inertia. So let's go look at our table for a rod rotating around its center point, and the equation for that is 1/12 ml squared. So we're going to stick in 1/12 times 15 times 2, the entire length of the rod squared, and we get rotational inertia 5 kilograms meters squared. And now let's stick that in the equation. So we have 5 times, the change would be 22 minus negative 8, so we're really adding 8 because it's reverse direction, divided by 120, and we get that that should take a time of about 1.25 seconds. Now I want to quickly note, we could have done this in a different way. We could have instead used I and tau, the torque, to solve for alpha, and then used a kinematic equation to solve for this change in time, and that's a totally acceptable way of doing things. This is just another way of approaching the same sort of problem. We've talked about Newton's first and second law, so we might as well move on to the third. So, remember, in regards to momentum, Newton's third law tells us that when we have two objects that are applying forces to each other, the change in momentum of one object, so delta P1, must equal the change in momentum of the other object, but in the opposite direction, so minus delta P2. Okay, well, let's look at that for regards to angular momentum. So if we have two objects applying torques to each other, the change in angular momentum of one object, delta L1, will be equal in magnitude the opposite direction of the change in angular momentum of the other object, negative delta L2. But you might recall that we used Newton's third law in talking about the law of conservation of linear momentum, that the total linear momentum of a closed system is constant, because if I include both objects in my system, if one of their linear momentums is changing, the other one must change by the same amount when they apply that force to each other, because that force would be internal. Now keep in mind that's only for a closed system, so in other words a system where the net external force is 0. You will probably not be surprised to hear that there is an angular form of this, the law of conservation of angular momentum, that the total angular momentum of a closed system is constant. So the angular momentum of the system before some interaction, so L of the system initial equals L of the system final, or the angular momentum of the system after this interaction. But notice, closed means something a little different now. Closed means specifically that there's no net external torque on the system, rather than no net external force. Well, this is all well and good, but we haven't really done anything new yet. But we're going to see that, particularly with the law of conservation of angular momentum, some things are going to change a little bit. Let's imagine this scenario here, that you are out ice skating. Let's say you're a very talented ice skater, and you are out here having a good time, and you start to spin on one leg around the rotational axis of your body, and you have your arms and legs extended when you do that. Now, quick note, I exaggerated this a little bit. Realistically, this leg would have to be underneath here to keep you balanced, but for right now, you're rotating around with some angular velocity, omega naught. And a lot of you know what's going to happen here because you've seen the Olympics before, that if this person, if you even, start to pull your arms and legs into your body as you're spinning, well, what's going to happen is that you're going to start spinning faster. We're going to gain angular velocity, and we're going to start spinning more quickly around that rotational axis. But why exactly is that happening? Well, let's investigate the scenario a little bit more. Let's first say, okay, well, what forces are there on you? Well, we've got the force of gravity on you, but there is no torque due to gravity because the force of gravity would be pointed downward, which is parallel to the axis of rotation, so there is no torque due to gravity. Well, you've got a normal force from the ice pushing upward on you, but there's not going to be a torque from that either. We might have a force due to friction, but we're on ice, so there's probably very, very little friction, so there's probably very, very little torque due to friction. So it seems that the net external torque on us in this situation is zero, that this would be a closed system from a rotational perspective. But if it's a closed system, that tells us that the angular momentum of this system will be constant, and that is crucial. So let's go ahead and rewrite this a little bit. I'm going to say, okay, well, my angular momentum is I omega, so I omega naught is equal to I omega. But we're missing something here. And what we're missing is that when so initially, we're rotating slower, and as we pull our arms in, we rotate faster. So there's definitely a change in omega, but is there a change in I? And the answer is yes, because as our arms and legs are extended, more of our mass is further away from our axis of rotation. So we have a pretty big rotational inertia. The mass is more distributed further away from the axis. As we pull our arms and legs in, that mass gets more concentrated along that rotational axis, and the rotational inertia actually goes down. So I really should say I naught omega naught, because not only does omega change, but I changes too. And in fact, they change in tandem. That as the rotational inertia decreases, the angular velocity increases. And then we could go the other way. If we were spinning and we push our arms and legs out, that would cause our rotational inertia to go up and our angular velocity would go down, because the angular momentum in this situation is conserved. So let's see what it can tell us about a different scenario. Let's say that my dog Sirius is standing on a merry-go-round, one of those rotating like playground discs, and that's rotating on a frictionless axle at 10 radians per second. And we'll say the rotational inertia of the entire system, so the merry-go-round and Sirius, is 100 kilograms meters squared, and he is going to walk, so he's pretty close to the center here, and he's going to walk towards the edge of the merry-go-round as it's spinning. And as he walks towards the edge of the merry-go-round, he's going to do that over a course of 2 seconds, causing the rotational inertia of this system to change by 25 kilograms per meter squared. And we want to, 1, determine the new angular velocity of this system, if there is one, and 2, we want to also say, okay, if the rotational inertia of just the merry-go-round is by itself just 90 kilograms meter squared, what is the torque that's exerted by Sirius on the merry-go-round during those 2 seconds? So let's go ahead and first look at the first situation. So as he moves out away from the axis of rotation, is this merry-go-round going to speed up or is it going to slow down? Well, in this particular situation, there is no net torque on this system, no net external torque, because the axle is frictionless, and gravity and a normal force wouldn't be applying a torque here because they're on the axis. So if that's the case, as he moves further away from that axis of rotation, the rotational inertia of the system increases. So initially, the rotational inertia of the system was 100 kilograms meters squared, but as he moves further out, it's going to go up to 125 kilograms meters squared, because we said it changes by 25. Because he moves further away, the mass is further away from that axis, this value must go up. Additionally, we said that the initial angular velocity was 10 radians per second, but we want to know, okay, what is the new angular velocity? But we know it must go down. And the reason why we know it must go down is because if the rotational inertia goes up, the angular velocity must go down to compensate and keep the angular momentum constant. Okay, so let's start trying to plug in some numbers. So I'm going to say, okay, we've got the angular momentum of the system initially is equal to the angular momentum of the system at the end. We're going to say, okay, I naught omega naught is equal to I omega. We're looking for the final angular velocity, so we're just going to divide both sides by the final rotational inertia. We're going to go and stick in some numbers, so 100 times 10 divided by 125 gives us an angular velocity of 8 radians per second, which does match what we predicted, that it would go down as he moves further away from the axis. Now let's look at the second question. We want to determine the torque exerted by Sirius on the merry-go-round during this 2 seconds it takes for him to walk from this position to the outside edge. But how do we know there even has to be a torque? Because if we look at our system, the angular momentum was constant. But now let's isolate the two pieces of our system, the merry-go-round and him. If we say our system is just the merry-go-round, well, if it's just the merry-go-round, its rotational inertia by itself hasn't changed, right? It's just 90 kilograms meters squared, and it's not going to change if he moves in or out. It's still the same shape. But its angular velocity has decreased. It's gone from 10 radians per second to 8 radians per second. So he must be exerting a torque on the merry-go-round, causing its angular momentum to decrease. Now just keep in mind that when that occurs, at the same time, his angular momentum must be increasing, because the change of the angular momentum of the merry-go-round must equal the change in angular momentum of Sirius. But now let's go ahead and calculate that torque. We have that delta L is equal to tau delta T equals I delta omega, and we're specifically looking at the torque on the merry-go-round. So we want to look at the rotational inertia and the change in angular velocity of the merry-go-round. So let's go ahead and say we've got those. We're going to divide by the change in time, and we're looking for this torque. So we're going to stick in 90, and then the change in angular velocity was 8 minus 10, and we're going to divide that by 2 seconds. And in other words, the net torque on the merry-go-round is negative 90 Newton meters. Now, what would be the torque on Sirius? It would be positive 90 Newton meters, and his angular momentum would in fact increase. So what are our takeaways on angular momentum? Well, one, can we define what angular momentum is? That's a measurement of rotational motion. And can we calculate using L equals I omega? Can we describe how a rotating object will move through space if it has no fixed pivot points? If we throw something through the air, it will rotate about its center of mass. And that center of mass will follow the normal parabolic arc. Can we describe what causes the angular momentum of an object to change, aka a torque, and therefore utilize the equation of angular impulse, that delta L is equal to tau delta T equal to I delta omega? And can we utilize the law of conservation of angular momentum to analyze how the rotation of objects with variable rotational inertia can change? So in other words, if the angular momentum of a system is constant because there's no net external torque, if that rotational inertia increases, if the mass moves further away from the axis of rotation, the rotation rate, the angular velocity, will decrease. And on the flip side, if we move that mass closer to the center, the angular velocity rotation rate will increase.